Hello Amir. So today I'm going to go over the lab 3 and the various solutions that I used to complete the lab. So essentially we had a few questions at the beginning just like the previous lab. So the answer for the first question about what does it mean for an arc to be consistent? So as we have learned, an arc is a relationship between two consecutive nodes. And let's say for example an arc like x, and the relationship is said to be consistent if each value in it belongs to the domain of x, and then there's some value y that belongs to the domain of y. And basically, that relationship between those two is satisfied. And we also learned about what it means for a network to be arc consistent. And for it to be true, essentially, every arc must be arc consistent. Not it can't if there's like three arcs, it has to be that all three has to be arc consistent. If it's just two, then that means no, the network is not arc consistent. So essentially, we also took a look at the arc consistency algorithm, and we learned that there are three possible outcomes. So essentially, the first one is if that one of the domain is empty, then that means there is no solution for it. And if each of the domain has a single value, then there is a unique solution. Now, if some of the domains have more than one value, then it means that there may or may not be a solution. We were also then presented with a CSP problem. So essentially, this one on the left was what we had to work with, and the constraints were mentioned where uh, essentially the values of a cannot be equal to b, a cannot be equal to c, and b cannot be equal to c. Now let's consider that we do consider the arc around AB, and we know that the value cannot be the same. So let's say we choose T in A, then that means we can't choose T in B. Essentially, we have to choose F. Now, let's say we also know that we are only considering one arc at a time. And since only a domain gets smaller when the value is not completely used, and in this case that does not happen. So essentially the domain of any variables does not get smaller in this case. Now, the next thing what we had is once the arc consistency finishes, it's a hypothetical situation, like let's say that all the variables have multiple values in the domains. Is there guaranteed to be a solution? So we also took a look at the possible outcomes of the algorithm just before this, and we learned that if some of the domains have more than one value, then there may or may not be a solution. So in this case, since no value is removed from the domain during arc consistency, due to the given constraints, a solution cannot be guaranteed. Now, essentially we had to create the same thing in AI space, so I went ahead and did it. So essentially, yeah. So over here, so I first created the whole thing, and I also set the values, I set the domain of each of the variables, and then I also set the constraints. So when I head over to the solve tab, and when I just hit auto solve, it just takes it by step. So essentially, as we discussed before, it checks each of the basically like relationship like separately, as opposed to just taking all the arcs at once. And essentially, it just goes one by one, and at the end, we do find that there is no solution for it, and it happens in around now. And so yeah, so I just wanted to demonstrate that this is what we have learned through this lab, and it helped me understand what a CSP is, what are the different outcomes of using the algorithm, and essentially the different approaches that can be taken around this. And this particular CSP was very helpful because it was not a straightforward one. We do know that these conditions do coincide with one another, so if you choose one, then it coincides with the other and basically cause a conflict. So it was a good one to work with. And so yeah, that's about it. I also attached the screenshots of the AI space problem that I've also used in this. So yeah, thank you.